And we have number 2 here. Now this just says predict the mode of radioactive decay for 2 different things, aluminum 28 and fluorine 18. And then it says identify the nuclide produced in each decay. So for number 2, we're going to, first of all, let's see, these are marked for some other problem because aluminum is element number 13. So we would look here at the number of protons, 13, and we would go up here and see where we got to aluminum 28. Well, where would we get to 28? Oh, this is marked as number of neutrons. So I need to take the 28 and subtract the 13. Yeah, okay, 28 minus 13. Maybe I better write this down. It's starting to get a little difficult. The aluminum is number 13 and we have 28. That would mean the number of neutrons is 28 minus 13, which would make it 15. Now I'm going to go back and look at the chart. I'm going to start at protons 13 because that's aluminum, and I'll go up here until I get to neutrons 15. And I see I am above the stable isotope. So this would be identified as neutron rich. I might have been able to see that by doing the 15 over 13 being greater than 1 since we're low in the table. But, it's better to use this because you can see that sometimes there's more than one that's stable. And so it's best to go to this when you can, if you have it available to you. So it's neutron rich, but it's also a light atom. It's not the heavy ones at the bottom of the chart. So we are expecting it, neutron rich tells us I'm thinking alpha or beta. If it's light, though, of these two, beta is favored. So this is what I'm expecting to be using, a beta decay. So that was what it said, predict the mode of radioactive decay. Now, it's also going to want to identify the nuclide produced. So I'm saying the aluminum 13 and 28 here is supposed to decay, forming a beta particle, which we know should be a -1 and no mass. And then I sit there and say, okay, 13 minus 1, that's 12. And then this would be 28. Oh, no, what did I do? 13 equals -1 plus 14. You'd think that would be simple, right? I go and I look up what is element 14. It's silicon. And then I go and I look back up here and I say element 14. 28 minus 14 is also 14. So I'm looking at 14 and by golly, look, it's green. So this is stable and we are done. We've confirmed that it was just one beta decay took us to a stable situation. Okay, now what about the other one? The other one says it's fluorine 18. I go look up where fluorine is in the table and it's element number 9, which means the protons are 9. And then I'm trying to decide what that's going to do. I will go to the chart because if I look at it right now, I say 18 minus 9, that's 9. 9 over 9 is 1, and I think, well, that sounds good because we said there was a line there, right? This line right here. But if I actually go to the chart, I find out if I go to 9 and 9, I'm below the stable one. So this is actually neutron poor. Then I'm going to be thinking about either positron emission or electron capture. I don't have a real good feeling for which one that should be. So I'm just going to go ahead and do both of them. Let's say that I took the fluorine and I decided I was going to do the positron emission first. Okay. Then I would write down the positron and I would say 9 equals 1 plus 8. 18 equals 0 plus 18. What's element 8? It's oxygen. And I go up here and I look at element 8 with 10 neutrons and I find out it's stable. So this would be a complete reaction. So this is stable with positron emission. Now let's try it with the electron capture. So that's still the fluorine and the 9 and the 18, but I am now going to capture an electron. Okay, 9 minus 1 is 8. 18 plus 0 is 18. Oh, it's the same stuff. How do I tell the difference between these two? Well, right now you can't. You would have to go to the lab and find out whether anything was emitted or not. Because this is capturing one of its own electrons. It's not giving off any sort of radiation, whether it's a particle or light. This is. You would have to take it to the lab and see if you detected something coming off when this occurred.